All yours.
Thank you so much. Can you hear me well?
Yes.
Yes.
Great. Can you see the slides? It's in its full, what do you call, display? Is that?
Yes.
Great. Thank you so much. Thank you, Pat, for not only invite me, but also give me a long set of homework, which I'm going to share with the audience. And I think the first question Pat asked me is about the difference between statistics and data science. And I have to say that I was very excited when Pat asked me to talk about that, because I actually, believe it or not, I actually have an answer. I think a pretty good answer for this question, mostly because, as Pat mentioned, that I served as the founding editor-in-chief of Harvard Data Science Review in the last 3-4 years now. And because of that, I got asked a lot about this particular question. So I do have some answer to it. And there are more questions from Pat about role statistics, about a collaboration, about data quality. You know, there's like 8 questions. And the one in red font.
I apologize for interrupting.
Good.
But the print on your slides is rather small. Is there any way you can make the visual larger?
Oh, this is actually the largest one. Okay, this slides, the next slides will be large. Okay, this one just to list everything. Yeah, my apologies. I'm trying to squeeze everything on one slide. And but let me just say that it's important to mention that Pat asked me lots of questions. I think this one with the red kind of a title is the ones I'm going to try to answer. The more black ones are the ones I really don't have much to say. I will touch upon a little bit upon. And just to give you a scope that this talk might be, okay, is this large enough? This should be large enough, right?
Yes,
okay.
Good.
And you know, I put in this kind of a scary font. So what is data science? And because I get asked a lot about that, you know, the correct answer is always it depends. In life, many times the correct answer is always it depends. The question depends on what, but you know. You know, some people think about, depends on who you ask, right? Some people think about data science is all about computer science, about machine learning, and others think about data science is what called a sexified statistics, and there are others even think about data science is BS, and they don't even mean you know, they don't mean Bayesian statistics, and so a lot more questions that has been asked, you know, for me and for others as well. What is AI? Does AI equal to data science? You know, what is machine learning? Is it machine learning a part of statistics? Do we still need a stat when we have so many data? You know, what does a data scientist actually do? And how do we train a data scientist? And of course, that's one probably some of you have been asking yourself, am I now a data scientist? What pay raise should I ask them? Ask them. The reason I list all these questions is except for the last questions, that most answers are in Harvard Data Science Review, and I'm not entirely joking about it because the Harvard Data Science Review was created trying to help to define and shape what data science should be. We published both research articles as well education articles. On top of that, we published articles about outreach to government industry. So obviously, I'm trying to advertise Harvard Data Science Review. It's entirely free, so please feel free to check, but not now. So let me start with the first editorial I wrote is really about data science, and I was thinking hard about launching the data science Harvard Data Science Review. How do I convey the broad scope of data science? So I wrote the first editorial. Talk about data science as an artificial ecosystem, and here's, by the way, is the printed version, the first volume of Harvard Data Science Review. If you want to get the printed version, I'm advertising. You can get on the website, and you can buy a copy of that. In this editorial, I basically trying to talk about data science not from what it is about, because it's very hard. It is very hard to define. But rather to talk about what is not. I was trained as a pure mathematician for a while, and in mathematics, if you cannot define something precisely, you define what it is not, right? And the basic theme I was talking about there is I want to emphasize data science is not just about machine learning or not just about statistics, Data science is not all about prediction. Data science is not only about data analysis, which is what statisticians are most familiar with. Data science is not a discipline that sits merely within the STEM field. STEM is, science, technology, engineer, and the mathematics. And my biggest point, which I tease you a little bit, not revealing yet, data science is not. I'm going to show you in a minute. So I used the articles in Harvard Data Science Review for this talk, so you will see quite a bit of those. And but first, let me put down like my view about what is machine learning and what is statistics. You may not agree with me, but that's the way that I've been thinking about. For me, like the machine learning is mostly about pattern recognition, and their major goal is to build emulators to mimic and predict humans and nature's behavior and their trajectories. On the other hand, the statistics emphasizing deciphering the variations and the model the simulators, right? Simulators are different from emulator. Emulator is just mimicking the kind of phenomena, the pattern recognition. Simulator, you really have to understand what's really going on, right? And so this is the obviously all these descriptions are subject to exceptions, and but I just want to put out there that the way that I think about what machine learning does and what statistics does have these two different emphases. Both are incredibly important. There's no pecking order which is more important. I think pattern recognition is incredibly important. We do many things in real life. We make lots of decisions, not necessarily we understand it, but we recognize the pattern. But on the other hand, someone has to understand what's going on. It cannot be the entire field is all about pattern recognition without understanding, with only rely on the black box, because as I was said, if we only rely on deep learning, somewhere we're going to get ourselves into deep trouble if nobody understands what's going on, right? And so let's just take this one quick example from the first issue of Harvard Data Science Review to talk about this idea of machine learning versus statistics. And in this particular article by Andrew Lo, who is the director of financial lab at MIT, and a great speaker. You should always hear whatever Andrew says, and many of you probably know him well. He wrote this article with his team about using the machine learning and the statistical imputation to predicting the drug approval. And they're not the first one to do this kind of study, but they were able to do it at the largest scale and get kind of most accurate answers because they combine machine learning with statistics, right? Machine learning is great that in terms of learning the patterns, they have over 140 features, 15 different disease groups. But there's one gigantic problem with these data, as any of you work on real data, real data are never really complete, right? I always tell my students that anytime you see complete data, you probably know somebody have already worked on it. And so the problem is that before their work, that people using machine learning, but they cannot deal with all these missing data. What do they do? People restrict themselves into the subgroup where they have complete data. Now, this is not only going to create a gigantic problem of reducing the sample size, but more importantly, you create a problem of a selection bias, right? As statisticians, we understand that, understand that well. So what Andrew and his group does is really to use the statistical models to do the predicting to impute these missing data. Now, by nature, by the default, this is the kind of work that cannot be done just by machine learning to learn the pattern, because you don't know what these missing data are. There's not much for you to kind of train your algorithm to do those things. And in fact, the data you have are biased because of selection bias. The more you train on them, the more bias you have, actually, right? So this really requires understanding the mechanism why these two missing data, model them, and they did like 5 different kinds of imputations. So this is just one example of how the two things combine. That after they did the imputation, they threw the machine learning algorithm to learn the broad pattern. So that's just an example of how two things combine. Data science is not all about a prediction, and if as a statistician, if we say so, that probably is not going to get much appreciation, because people will think about ourselves being self-serving, because we're the field to talk a lot more about inference than prediction. But here's the article from industry leader Nathan Sander, who used to be the chief scientist at what's the company? I forgot actually. At Warner Brothers. And so he really wrote article about, this why the industry needed this balanced perspective between the prediction and the data science and the inference. So you think about both the pattern as well as understanding the mechanism. And I also want to say data science is not just about data analysis, which is the one as a statisticians we learn the most. And here is an article again in the first issue of Harvard Data Science Review, written by a computer scientist, a leading computer scientist, Xiao-Li Meng. Currently, she's the director of Data Science Institute at Columbia, who wrote her famous paper. One of them is on the computational thinking. So Xiao-Li, wrote this short article laid down from a computer scientist perspective. What is what she called the data life cycle? And this is just not about the analysis is only one part. And again, I apologize for the small font here, but let me read through them, right? The idea from Xiao-Li was you had to think about data generation, collection, processing, storage, management, analysis, visualization, and interpretation. Now, statisticians are probably familiar with most of them, and we're the one probably worked the most hard on the analysis and on the collections, right? We work much less on processing, storage, management. We're increasingly working more on the visualization. We certainly emphasize the interpretation as well. But you can see that the data analysis is only one part of this whole data life cycle. Now, I have to confess that initially when I got a genetic article, I said, great, this is terrific. This covers everything about data science, until I invite two more authors, one from philosophy, one from social science. And you will see how they enriched this picture, right? By the way, here is a very good definition of, at least a working definition from Jeanette about data science. I do find that's very kind of concrete and does capture most of the essence. And of course, no definition of data science will be complete, but here's one. She viewed data science as a study of extracting value of data, and she has certain explanations what these value and extracting means. Again, I encourage you to read these articles yourself, complete free online. And so the philosopher I invited, this is the whole point of data science is not a discipline that sits merely within the STEM field. And so I have this, the middle article was from Jeanette, and I arranged this way because the philosopher actually remind us, and this is a philosopher of science, Sabina Leonli. I hope I don't butcher her name too badly. And she really wrote this article emphasizing the conceptualization of the data is so important, right? So, and it's also very interesting that every kind of a discipline has their own diagrams about the field. You have seen Jeanette define everything in terms of this kind of a process. And what's interesting as philosophers, they define things not in terms of the process, but in terms of concept. And I think this cycle was particularly interesting for me, at least, that for Sabina, there's nothing to start. It's a circle, right? Data are ordered as model. That's very interesting. A concept that data model is merely to reorder these data. Models are interpreted as knowledge, and the knowledge inform further of interaction with the world. The interaction with the world produce the object, and the object process as data. So that's just a philosophical view of the whole kind of data science, cycle. And I thought it was very refreshing. And I think, I certainly would not be able to come up with the concept of that. Although after read, I feel like that's really, quite good. I also strongly recommend her new book, Data and the Society. And you will learn why we use data as singular form, why we use data as a plural, what's the difference between these two. And it's really quite interesting. I want to emphasize this is like, for me now, data science really started from philosopher. And I guess anybody would agree that all these things she's talking about is right at the heart of data science. She also wrote a book on the data-centric, biology. So that's at the very beginning, think about conceptualization of the data. Her point is there's no such thing as raw data. And to the other end, I invite Christian Borgman. Some of you probably know her as well. She reminds us that there's another really big topic which is missing from Jeanette's picture as well as missing from Sabina's kind of emphasis, is really this whole idea of the afterlife of the data. The idea that you need to record the data. You need to talk about curation. Particularly thinking about these days, we emphasize replicability of studies. Reproducibility. Like, how do you put down everything you have done, all the judgment you have made, so others can look at what you have done and in the future, right? And that's not easy at all. And it's very interesting that they have their diagram. DCC is a digital curation center, I think. Yeah, and it's very interesting that they have multiple cycles, there are concepts, there are actions. It's certainly a little bit more complicated, but this is not the kind of diagrams that a statistician in computer science will come up, because they talk a lot about the curations, preservations, appraisal, select, receiving, and all these issues are, in the broad sense of data science, is really very relevant. And she wrote another wonderful book I would recommend called Big Data, Little Data, and No Data. Okay, so I just want to give you this kind of broad sense of what the data science is in this when we think more broadly. The key point I want to make is most critical data science is not even single discipline by itself, and that's my answer between what is a statistic, what's the relationship between statistics and the data science. There's actually a real consequences of realizing this. So I certainly have been quite vocal, and others have as well, that we probably shouldn't create the Department of Data Science. Okay, the point I want to make is just by acknowledge, right? We know there are science and that there are scientists, but we rarely hear a Department of Science, unless you're in a very small kind of a college, probably don't have enough resources to put everything into one department. Similarly, there are social science and a social scientist, but you rarely hear people talk about Department of Social Science, right? Similarly, you have humanities and the humanist, but a few Department of Humanities. And this one got myself into trouble. I was giving this talk, a part of it in Cambridge, the real Cambridge, and I said they're engineers and they're engineers, and you rarely hear the Department of Engineer. And right there was a Department of Engineer, it's, at least in England. But I think you get my general point here that data science itself is just like a science. Itself is a collection of, it's like a natural science, right? Natural science is to study physical science, for example, is study this inorganic world. And data science to me is a collection of disciplines study the digital world. And so the relationship between statistics and the data science is very much like the relationship between physics and the physical science, or the sociology and the social science. I don't think people will mix these two. Social science is obvious. Sociology is obviously a leading pillar in social science, but nobody will say social science is all about sociology, right? So I think that's the way that I think we should view as statistics and the data science. Then that leads to the question is, what is AI? That's another confusing word, because these days, particularly in media, AI it's always confused with data science itself. People using these words exchangeably, and the answer here is it depends on what the meaning of the word is. And for those who are old enough, you probably know where this sentence is coming from. But the serious point is that because AI was about imitating human intelligence, right? It was really about, how do we create the machines can think like a person? But now AI is essentially like machine learning, or anything media perceived as from computer is become AI, right? And here's a great example. The first issue of Harvard Data Science Review published an article by my colleague Mark Glickman and his team, and I think Mark gave a public lecture at the ASA about using data science or statistics to kind of settle these dispute on these authorship. Well, guess what happens once this thing gets media attention? Well, here's one of the articles, right? The media immediately called this is called artificial intelligence. And in fact, as Mark can tell you, all did he do was simply running some logistic regressions, Bayesian logistic regression. He didn't look into all kinds of random forest or other techniques, machine learning, but in the end, it settled with kind of logistic regression. Now, as a statistician, we probably would never consider ourselves doing artificial intelligence if simply running a logistic regression, but that's how the public, viewed using this term. And but if you really want to trace the history of artificial intelligence, the original definition you can find in this plaque, which is I think in Dartmouth. And I got to know about this, and it's really because an article I'm showing a second in Harvard Data Science Review. But it's important to actually reread what initially how these people think about artificial intelligence is to proceed on the basis of conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that the machine can be made to simulate it. So this was original artificial intelligence was quite clear. They're trying to have a machine to mimic how human thinks. I don't think we're that yet. We're that yet at all. This is an article I want to mention that by Stephanie Dick, who is a co-editor for the column called Minding the Past for Harvard Data Science Review, and she wrote this wonderful historical review piece about artificial intelligence, and I certainly encourage you to read it if you are interested in the history of AI. The article that we also published in the first issue of the Harvard Data Science Review was by Michael Jordan, and this article has been getting lots of citations, lots of attention. He really talked about what he called artificial intelligence. The revolution hasn't happened yet, and so his big point, as he put it, AI should be about one is the intelligence augmentation, meaning that we use the idea is not just to mimic humans' intelligence, is to beyond it, to do better than the human can do. So his point is that he has 2 points. One is it should be about, instead of AI it should be IA. It's the intelligence augmentation. It's using computation and the data are used to create a service that augment human intelligence and creativity. All right. So that certainly goes beyond the original goal of the AI. But the most probably importantly is his point about intelligence infrastructure. Right. What he meant is that we need to create a web of computation, data, and a physical entity that exists that make human environments more supportive, interesting, and safe. And that's where I think all these fits very nicely, right? You probably have heard about, now we're more and more talk about IoT, the Internet of Things. Then you have IIoT, the industry Internet of Things. Then you have IONT, it's the Internet of Medical Things. Then you have the Internet of Battlefield Things. That's for the military application. You also have the OOT, the Ocean of Things. All these are really fits what Michael Jordan is talking about, intellectual infrastructure. These all has physical things connected with the digital world through computation, through data. And I've said maybe the most concrete example for you guys, since you're doing transportation, is the CAV, right? Now I want to mention, I'm going to talk. Next slide is about CAV. I want to just preface what I'm going to say. My knowledge about CAV is extremely limited, and the only reason I know a little bit about is really, or I had to do a little bit of reading, is because in my role as editor in chief, I had to handle papers that are on this topic, okay, which is obviously incredibly relevant for Harvard for data science in general. But I decided to talk a little bit about it just to give you one data point, how the general public understand these issues. I'm sure what I'm saying will be incredibly shallow for you guys, but I thought it would be useful to provide one data point that so you can see how the I'm not claiming myself as representative of any populations, but at least one one data point. Okay, so I search online and find these are very useful very diagram. But I thought it was very interesting to me because first, as a lay audience, I initially just only know the phrase of what do you call the self-driving car and what do you call the driverless car. Later, I also learned these two terms have a little bit different meanings. And so when I initially learned this whole idea of a connected vehicle, I thought, oh, that's really quite interesting. That's something like I don't think most people understand, because these are the idea of the vehicle talk to vehicle, vehicle talk to infrastructure, vehicle talk to pedestrian. All these things are really make them much more like an iPhone, right? Instead of just isolated, just as a transportation device. And I think I just steal this from Minnesota's state website. I still don't know which phrase you guys prefer. I heard there's automated and autonomous, and I know there's a little bit difference. Autonomous supposedly to be capable of making its own decision. Automated is more kind of follow the human direction. That's what I read. But whatever it is, that for me, what's really interesting is this idea that we're not just talking about a car anymore. Very much like a phone, iPhone is no longer just a phone. It does so much more. So that got me really thinking about the car. CAV to me, to the physical world, I think it can be really more than a smartphone to the digital world. That's the way that I start to appreciate this. And I started thinking about what are the big dimensions that CAV is going to impact, right? And just like the phone now do so many things. So as I started thinking about this kind of broad picture, and I realized something quite interesting, because it's going to touch on energy, time, money, space, all those things. And I want to tell you that it's kind of funny that initially when I started thinking about what are the dimensions I should put down, I got reminded of a joke, as some of you probably have heard about. It said, the joke says, it's actually not really much joke. Now I'm getting older, that I started really appreciate it. It said, when you are young, you have energy, you have time, but you have no money. When you become middle-aged, you have money, you have energy, but you have no time. But when you're getting older, you have money, you have time, but you have no energy. So that, to me, like the time, money, energy are three most important things. So I put that down first. Okay. So this is kind of when I was reading various literature, trying to understand what are the big issues, or big impact the CAV will have. Now, obviously, the first is is about energy, and of course there's a money. There's time, and particularly interesting, I got reminded, it's not just the travel time is shortened. You have this what's so-called productive commuting, because you in the car or in this whatever this thing is, that you can conduct meetings, you can relax, you can do, if you can relax, I mean, you can do all kinds of things. I also got reminded about, there's got to be a lot of issues, a lot of impact in terms of space, right? You certainly have a reduced parking space. I think that's one will be very much welcome, but there's also reallocation of the road space, so on and so forth. And I, understand there's definitely safety issues. Then there's, helping people who cannot the mobility is more kind of increase your autonomy. But I think that we should start thinking about autonomy in the big term, right? Like energy independence is another form of autonomy as well. Privacy is a big issue, obviously, because of this. Now we could essentially you have in principle, you have a surveillance of where people will be about, right? In any kind of movement. And the last one, it's not last one, there are many more than this, but these are the ones that I give some thought on it. I think that this security issue is really interesting. And most stuff I've read is about cyber attack. And I really think about, we should also worry about physical attack, right? And this is the issue that I don't think it's just the issue of whether that will happen or if that will happen. I think it's just when. Cars or vehicles being used for criminal activities are it's not a hypothetical, right? We see how the cars were used driving the crowd, car used to deliver bombs. And so I thought, the issues like that. I thought about that. It's just thinking about how do we do data science studies for these issues that we probably don't have much data on it, but it's obviously very important. Once the car is as it perceived as self-driving, I can see how, just like we use all these technology to benefit society, but the other side, the criminals always take advantage of the technology to deliver whatever they want to deliver. So I think that these issues that should also be really considered. the reason I really thought about that is really because I said, well, how do I even think about the data to study those problems, to anticipate these issues. So the data science challenge and opportunity here is, this is almost cliche to say it, but I guess you all understand it so well. There are way too many factors, right? I start thinking about it, because you have so many goals. You want to improve the energy consumption. You want to, increase the safety. You want to, certainly save the money. You want to help people to move. And but we just have, I see we have done lots of study. I know the DOE's, smart report seems to have done a lot, but it started from reading the report. I realized, and I think I anticipate that it's just way too high uncertainties in many things in terms of like the consumption of the fuels. The one thing I read was I saw that that's a really interesting problem with what they call the ZOV, right? The zero occupancy vehicle. Once I read, I said, yeah, obviously, humans are pretty good at taking advantage of whatever is being offered. The whole idea is to reduce the kind of unnecessary travel, but you can see why when it can drive self, people can use it to reposition the cars or to deliver goods without going there. And then suddenly, according to these studies, that now you actually have more consumption than you're trying to reduce, right? And that's incredibly interesting. And how do we? And I saw the studies about trying to provide incentive, like 33 cents per mile or whatever it is, trying to reduce the cost, trying to discourage that kind of behavior. But those things are, really important to study. And I want to mention, and this is related to the second part of my talk. I'm get a little bit more specific on the data quality issues. Whatever these studies are, I think that here we really have to make sure they're representative if you want to estimate that the future real impact, because these studies conducted in these more experimental settings can be very selective, can be very biased, and I'm going to show you in another content in terms of estimating the vaccination take in the United States, how these selective studies creates really very different answer, from the reality. So one kind of my pitch here is for whatever study here, particularly those for estimating global consumptions on national levels, even state levels, that make sure that thing will be representative is really incredibly important, at least to understand where these bias come from. And I'm going to say a little bit more later. Okay. So I also want to mention that that article by Michael Jordan was a discussion article. We invite lots of experts, but interestingly, when Michael Jordan wrote his rejoinder, he really make this good point about AI is no longer just about mimicking humans' brain. He's talk about a marketing, to talk about economic system. It's really trying to take this much more broader view of what, where we can learn from. And the point I want to emphasize this is, again, the whole data science space is become really very broad. And we statisticians particularly should really open our mind as well, and to really think in these broad issues, and particularly training the future generations to think broadly as much as possible. So now let me switch to talk two issues that I think is a grand challenge for all of us, and I call them the permanent challenge for data science. And for both of them, I've done some work, so I'm going to speak a little bit with a little bit more kind of a methodology kind of angle. One is the data privacy. Okay, and I would say data privacy, it's a forever, it's going to be, it's going to be challenged. There's no way that we will ever get rid of this issue, because I'm sort of half joking, half serious that how we humans that we kind of all like to know what other people do, and we don't like other people to know what we do. So, but the only problem, other people are us. So there's just no way to there's no way to really really get it wrong. So I wrote a point for you to remember this issue. I said, data born to reveal, privacy requires us to conceal. So whether you like it or not, it's always going to be a big deal. To me, the phrase data privacy is almost like oxymoron term, right? Data is to reveal, privacy is to conceal. So you can see that term itself is forever going to tell us that we will have a big problem to deal with. It's all about a compromise. Now, the other issue is data quality, right? Data quality, I think that any of us, particularly any of us analyze any data, what we all want is, we all like to have a large amount, clean, highly informative, easily accessible, publicly available, routinely analyzable, clearly interpretable data, right? That's all we want. Like everything is very easy to do, lots of information. You have no complication. Well, in reality, we typically get any important problem you work on, you'll be getting messy data with low unknown quality. If one's lucky to have the relevant data, often you may not even have data. The one I mentioned previously, I thought about a lot of issues there for the CAV is really about to find the relevant data when you cannot do experiment on it. What would be the problem? What would other studies can inform that? So let me talk about a little bit of differential privacy. I did some work thanks to my former student, Robin Gong, who is now currently assistant professor at Rutgers. And if you ever want to know anything about data privacy, particularly differential privacy, she's one of a very clear speaker, I've thought a lot about. You certainly should invite her. So she had been working with the Census Bureau a bit and on this differential privacy. And I'm going to just talk a little bit about differential privacy here, both as a quick introduction, because whether you like or not, this term is coming. And the other day I reminded when I look at my iPhone was trying to convince me to use their Apple's analytics, and it has a phrase there say, what data are protected by differential privacy. I was laughing hard because I know what's really going on here. Is it really protection? We'll see. But there are a couple of articles in Harvard Data Science Review. One is written by Census Bureau about the implementing differential privacy for the 2020s, 7 lessons they've learned. The other is by two social scientists talking about differential privacy, social science, and the urgent puzzle. The urgent puzzle here is anytime you're trying to protect the privacy, you basically make the data harder to recognize their pattern that obviously has impact on the quality of lots of social science study because they rely on data to really give them the information. So the whole idea of differential privacy for 2020 census, the leader is John Abel, who's really leading this terrific effort. And I said in many places, I think Census Bureau really should be thanked for doing a heroic work, because they're the ones told to collect the data as accurate as possible, mandated by the Constitution. But then there's also Title 13 say you need to protect privacy as much as possible. They're basically given this almost impossible problem. To work on. The whole idea of differential privacy is getting very, a very popular notion, and my colleague, both in computer science as well as in my own department, Cynthia Dork is the one, and her team have been credited for really pushing this concept of differential privacy. So now let me give you a slightly kind of a technical definition, because it's important to understand what's going on here and why there's a really big data science problem in the broad sense, not just for computer scientists, not just for statisticians. Cynthia Dork herself is a computer scientist. John Abel is a economist, and so here the whole idea of differential privacy is saying that if you ask me to produce you, let's say, computer sample mean for me, I will be adding some noise to it before I release to you. So this MD now become a random map. Now, in the differential privacy original definition is very interesting. The data is entirely fixed, okay? It's not like a statistician about that model. No, data is fixed. This is very much like those of us working in survey literature, thinking about finite population. The data is entirely fixed. There's nothing random about it at all. I don't make any model assumptions, but I'm going to inject a random noise to it, right? So the idea of differential privacy is the following idea, saying that if you compute this answer, let's say sample mean, so the two data set, one is, for example, have me in it. The other one is I'm not in it, okay? And I do these two means, so they might be a little bit different, right? And then I'm adding enough noise to the answer before I give to you so that probabilistically that you can't really tell whether I'm in it or not, or the answers that my own answer, own numbers that will have very little influence, to this, to what you get. Now, this may or may not be always true. The idea is you adding enough noise to make that true, right? If I make a ton of noise, like make a noise, then in the end, nobody can recognize anything, right? So this technical bound is to the e to the epsilon, and if you don't like e, think about 2.7. okay, and to to the epsilon. And the key idea is why it's called differential privacy. It's really a derivative idea. It's taking derivative with respect data in some sense. You should take a 1% out. If you ever remember, that the epsilon delta language for taking derivative, you make a small perturbation, right? So the idea here is that for statisticians, we may recognize this immediately. This is essentially trying to bound the likelihood ratio when you think about data, the origin data themselves as parameter. Okay, the origin data here is a target. Remember, this is not a statistical notion to start with. It's the computer scientists want to protect the data in the worst case. So I talk to Cynthia. I say, Cynthia, how did you come up with notions like not thinking about the model of data at all? And Cynthia said something to me was I think it was really true. She said, Xiao-Li, you statisticians worry about average case. We computer scientists worry about the worst case. Okay, so this is really about a fixed data set and how to protect every single data set. So you will also hear there's something very common. People talk about something called the Laplace mechanism. So what does it mean? What I mean is really the following. Suppose the QD, let's say it's a sample mean you want to compute, but before you release the sample mean to the person asking you the data, you add a Laplace noise. Laplace is just it's here the curve. Right? The blue is the normal curve, and this red is Laplace curve. Essentially is a back-to-back exponential distribution, and you multiply by something called the global sensitivity of the Q, like how sensitive is your measure of your query itself, and divide by epsilon. Epsilon is that amount that you want to inject in, right? So mathematically you can show that by doing so, you can guarantee this. Okay, so this adding Laplace noise with these two quantities is to guarantee this happens. So intuitively, this also makes great sense, right? Because if something's very sensitive to individuals, then it will take a large epsilon to protect it. Okay. And so here the larger the epsilon, the less. Sorry, I said it backwards. The larger the epsilon, the less protection. If epsilon go to infinity, there's no protection. Okay. So epsilon here is called the privacy loss budget. So the larger the epsilon, the less the protection. If you put the epsilon equal to 0, which means you're adding infinite noise, okay, which will be completely protected. But then of course the data will be useless, right? And so this original idea used the e to the epsilon is because if the e to the epsilon is approximately 1 plus epsilon, if epsilon is small, that's kind of the standard Taylor expansion. To tell you, like, you think about epsilon, it's 10%. It's like a plus minus 10%. But unfortunately, getting larger and larger. And I think the last time we heard, Census Bureau is now contemplating using epsilon equal to 19. Now, equal to 19, e to the 19 is 178 million. Okay, now think about how large this number is. Now, why that is the case? Why the Census Bureau gets pushed, this epsilon, gets so large? Well, there's the issue of the trade-off between the utility and the privacy protections, right? Because when they do these studies that the finding, for certain minority group, the epsilons, it's too small. You have to increase the epsilon in order for the data to be useful. But this actually turned out to be an incredibly interesting challenge. It's a question I want to pose to the general community. Who should decide the epsilon, right? That clearly shouldn't be the job of statisticians or computer scientists, because that has so much consequences in terms of to the society. So I want to just make clear that people understand this notion that the differential privacy or any privacy, they don't really fully protect your privacy. Nobody can. If you put everything, if you put everything about yourself on, on the Facebook, nobody can protect you. This is from my ex-boss. Steve had this great line. Said the only sure way to protect your privacy is to make sure no one cares about you. Okay, that's the only sure way to protect your privacy. But I also want to make sure that people understand that the differential privacy was trying to protect what's called increased disclosure risk. The idea is, whatever people already know you, by releasing my data, I will create additional a risk for you, right? So it's going to it's it's going to control that. But it does not fully eliminate it. No method can. So it does it with certain epsilon, and when the epsilon gets too large, it does not really protect you that much. The one thing about differential privacy that it provides a very theoretically it's a great framework, but we should also keep in mind these theoretical guarantees are only theoretically. That in practice there's always deviation from what the theory should say. But there's one crucial message, and here this is the one I think statisticians now can play a really incredible role here. Important role is the differential privacy data should not be analyzed as real data because their noise has been injected. In the next few slides, I'm going to use some slides provided by Robin to show you the danger if you just analyze as if they are they're real data, right? There's also really interesting thing that if the differential private data, if you analyze it properly, that actually can lead to fewer false discovery because what differential privacy does is to force your methods to be robust to individual changes. So although your method may not be robust, by giving you the data that has this protection, actually force your the consequence of that is actually to be robust to this kind of, so this is kind of an unintended consequence, which itself has both plus and minus, right? It's like a power issue. You have too much power, too little power in terms of hypothesis testing, and there is this trade-off between type 1, type 2 error. But in this domain, that I think it is important that we these days have too many false discoveries because people are kind of just doing selection too much, and this actually forces you to do some robustness. Now this one is half joking, but I'm also half serious. DP data created many research opportunity, right? Great news for those of us who want to be poor and famous. Okay, so you can do a lot of research here. So many questions and many contributors and the stakeholders think about this differential privacy. For a given privacy loss budget, what are most effective ways to privatize the data? I mean, these are questions I think the computer science thought a lot about. And statisticians coming in talk about the roles of statistician. That what method and skills do we need to extract maximum value information from privacy data? And I would say that we have the tools available already. We just need to kind of make people aware of them, right? In what ways and to what degree does privacy protection affect the utility of the data? And I think that's a question of all of us need to study. But the most challenging question is, and who should be given the great responsibility to set the privacy loss budget and how to allocate it, right, into different groups. And that comes in with ethical studies, social science, policy study, legal studies. And I really said that, I hope that neither statisticians nor computer science will be given the job to say, you decide epsilon. And I think that would be pretty bad, okay? And it's certainly in your study on the CAVs, I know your data quality, data privacy is very important. And there's, I'm sure, you'll be setting up these epsilons in talking to a lot more stakeholders than just decided by an engineer or by a computer scientist. Okay, so here is a quick example about how this thing will impact you. Suppose that you're running a linear regression. Okay, now the data itself is no longer y and x. Each one is already adding some Laplace noise. Okay. So if you just blindly just say, okay, I just ignore the noise that has been added, if I just going to analyze it, treat this differential private data as if they're real, your estimator, as you probably guessed, your beta 1 estimate is going to be smaller by that because you're adding noise to the both predictors, both covariates and outcome variables. The correlation goes down, and therefore your beta is going to be smaller. The interceptor itself can up and down, depends on the problem. Okay. Now, so here is an illustration. All these slides are coming from Robin. That the simulations here is that we know the truth, and here's the 95% confidence regions for both beta 0, beta 1s. So when you know the truth is without any data privacy, when you do these confidence regions, they cover nicely. And when you're adding a little bit of privacy protections, and if you just ignore that you actually have the noise added, you started seeing these intervals these regions start to be moving, and this one is epsilon gets smaller. You have more protections. Then this thing move away, and you can see, as I said, the beta 1 gets too small, right? So now, like when epsilon goes to 0.1, if you analyze the data as if there were nothing happened, you will never get the right answer. Okay. This is, you never get right because it's, you're so biased. It's, it's out. Well, the good thing about this differential privacy methods is that it's very transparent. It tells you exactly what kind of noise has been added. It's a Laplace noise or some other noise. So you know what the model is, okay? You will not be told what the value added, because otherwise defeat the purpose, but you will be told what, what the mechanism is. Because you have the mechanism, you can write down, right? For statisticians, that's just like a convolution problem. You were told how what the model of the data should be. So you can integrate out whatever you can do the likelihood method, you can do Bayes method, whatever you're doing, here you can do this calculation, and there's all kinds of research you can do to do this thing. Well, so here's the illustration of how this thing works. This is the original truth, and the green ones are using the differential private predicted data, but analyzing them correctly. Okay. Now you can see the green ones at least, start to have a chance to cover the truth. They're not as good as the unprotected data, because we know there is a loss of the information. The intervals are wider. It's this one missed it. This one is there, but you can see they are much better than you just blindly estimate using data without realizing these things have noise added. It's a very simple one. For statisticians, this is really a great area for us to jump in to create a software, all kinds of problems to work on, because we know, we know what's going on. Okay, I have 5 minutes, so I'm going to talk very quickly the last part about the data quality issues. Okay, I did an article back in 2018 about estimating these kind of data quality itself, and the biggest point I want to make is that statistics or statistical errors have been always emphasized to only depend on the sample size, not the population size. But I've been pushing this notion that we should worry about the population size when you have selection bias. And this is a very quick way to understand why we don't need the population size when you have randomized the sample. When you mixing a soup well, right? If you want to test whether it's salty or not, all you need a few small spoons. It doesn't matter the size of the container as long as you're mixing well, because the homogeneity, because the representativeness. In general, you don't have that, but the probability sampling ensures that randomization is to make it statistically mixing well, right? So the question then is that when we cannot do a representative sample, or when these big data come in on their own ways without any quality control, what happens to our errors? So this was the identity that I used in my 2018 article. Because of time, I'm just going to go very quickly. Essentially, it said that you have to worry about not only the variable of interest, but also whether there's somebody in and out of the study or not. So R is the indicator. For people study missing data, this is a very common a notion of sampling. It's a sampling indicator. It turned out that you can write down very simply that the difference between the population mean and the sample mean equals the correlation between X and R, and a quantity determining the sample determining the quantity, as well as the problem difficulty. Problem difficulty here is simply the homogeneity of your population, right? If everybody has the same opinions, you only need to sample one person. But the key issue, the key quantity I want to talk about is this correlation, is how correlated somebody is in the sample that are correlated with their answer. And we know randomized sample will destroy this correlation. So therefore, make things representative. But if you look at your answer, say, because I'm going to vote for Trump, and I know that's not a popular answer, I'm not going to respond, you can see how you induce the bias, right? So so that's the formula, and it's very easy to derive. I'm not going to show that. So I want to show you the consequence of that. In real life, for 2016, 2016, election, that afterwards we know the answer, so you can back calculate what that correlation is. And it turned out the back correlation that for 50 states plus DC, we have 51 data points. I can look at the histogram of that correlation, right? That correlation essentially models the behavior when people respond or not. That for Clinton's answer whether voted for Clinton or not is centered right around the 0 as it should be. But for answer whether voted for Trump or not, that actually was centered about like 0.5%, right? But you see the thing moving away from 0. What's the consequence of that 0.5%? That's a scary part. The consequence of 0.5%, and I'm going to stop right after that. You can calculate what is the effective sample size of your data once it suffers some data defect, let's say measured by row. You can show that the effective sample size, meaning that if I've used this data to do my estimation, it's a statistical error is going to be equivalent to a simple random sample with the same effective sample size. So in this particular case, I look at, if you take a 1% of the US population, voting population, which is about 2.3 million people, that if you have 2.3 million people, which is about like 2,300 polls, each with 1,000 people in it, you think you have opinions from, you know, this many polls, and if they all said you're going to vote for Clinton, you probably say, well, that's pretty safe. But unfortunately, if you do the population, if you do the effective sample size calculation, you can show the effective sample size is equal to about 400. Okay, that 0.5% correlation basically destroyed essentially 99.98% of the sample size. It's not surprising because everything is dominated by bias. When the sample size is so large, the sample variance itself is really minuscule. Everything is dominated by by the bias. When you turn that into it, and that's that's what happens. So let me stop right there because I want to give people warning about the importance of the data. The importance of the data quantity that if you don't, okay. Yeah. Okay, let me just stop there. Because next example is.
Am I calling it 4? Is that okay?
Is
Sorry,
the
I've got this meeting's going long.
Okay, I'm done.
Okay, so I'm